So this is a screencast that's going to go through the Unit 3 Graphing Toolkit. So first off, we have three different types of graphs. We have position versus time graphs, velocity versus time graphs, and acceleration. And there's sort of three parts of the graph that we look at, and some of those have a meaning, some of them don't. So we look at the meaning of the slope, meaning of the y-intercept, and meaning of the area under the curve. So for position versus time, meaning of the slope is velocity. We know that from before. The meaning of the y-intercept is the initial position. We don't have a meaning of the area under the curve for position versus time. Velocity versus time. The meaning of the slope, we learned that from our lab this unit, is acceleration. The meaning of the y-intercept is initial velocity. And for velocity versus time, the meaning of the area under the curve is the displacement, or the change in position. Another way to say that is delta x. So for the position versus time graph, to get the velocity, you do the slope. For velocity versus time graph, to get the acceleration, you do the slope. And then kind of going backwards over here on this side, velocity versus time graph, the change in position gives you, or the area gives you information about the graph before it. So slope gives you information about the next graph. Area under the curve gives you information about the previous graph. So acceleration versus time. This is a new graph this unit. The slope for our acceleration versus time graphs, they're always going to be horizontal. They may be piecewise, but they're going to be horizontal. So we don't have a meaning of the slope in this unit. There is an actual meaning. It's called the jerk, which is the change in acceleration, but we're not going to talk about that this year. The y-intercept as well. The y-intercept, since it's not it's a line with no slope, the y-intercept doesn't really have a meaning. If it did have a slope, as you may figure out, we'd call that the initial acceleration. That would be the y-intercept. But since our acceleration versus time graphs are just horizontal, the y-intercept doesn't really have a meaningful meaning to us. It does have an area under the curve, and that does have a meaning. And that meaning actually gives us the change in velocity. So velocity versus time gave us the displacement, or the change in position. Area under the acceleration versus time gives us the change in velocity. Let me explain why that is. So if we have an acceleration versus time, so the units are seconds. For acceleration, the units are meters per second squared. And we have our acceleration graph. If we want to find the area under here, just length times width. Well, the width, or the height, however you want to think about it, is acceleration, and the length is time. Well, acceleration has units of meters over seconds squared. So this side here would have units of meters over seconds squared. This side here would have units of seconds. So we do meters over seconds squared times seconds. Our seconds are going to cancel 1 second on top, and then since there's two of them on bottom, only one of them, we get meters per second. And these are units of velocity. So the area here gives us the change in velocity. And if it's a negative area, so this would be a negative area, this would give us a negative change in velocity. So on to looking at stopping. You'll notice here I didn't put a line across for the t-axis, because it doesn't matter if you're in a positive or negative position to be stopping. It's just what the graph looks like. We have a curve here, and it stops right here. Remember, to get the instantaneous velocity on a position versus time graph, you find the slope of the tangent line. And if I draw a tangent line in there, you can see that that slope is 0, so it's stopping velocity of 0. Similar thing here at sort of the peak, at the maximum of the parabola. It's the slope is going to be 0 here, so the object is stopping. On a velocity versus time graph, it looks a little different. Here we have an object that's going positive direction, but going slower and slower and slower. When it hits the t-axis, the velocity is 0 right here. There are numbers on here that would say 0. So right there, the velocity is 0, so it's stopping. Turns around, goes the other direction. Same thing kind of going the other way. When it hits the t-axis, velocity is 0. Here we have an object that's moving forward slower and slower, and then moves faster in the same direction. So maybe it was slowing down, and then right here he saw that the light turned green, So then he hit the gas again. This does not stop. You have to hit the t-axis in order to stop. You have to hit this spot where velocity is 0. Here, maybe the velocity is 1 meter per second. That's not stopping. So this is not an example of stopping, but it's a common trick, a common mistake that students make. Turning around. Again, no t-axis because it doesn't matter where you are when you turn around. So we have a curve. At this point here, the object is, the position is decreasing, and now the position is increasing. It's going backwards, now he's going forward, he turned around. Same thing, kind of the other direction, going forward. Now he's going backwards, he turned around right here. Here we have an object that's going forward faster and faster. Now he's going slower and slower. Maybe he stops right here, he goes real slow, and then he's going forward faster and faster. Notice his position is increasing the entire time. He's always going forward. This is not an example of turning around. On a velocity versus time graph, here we have an object going forward, so it's the positive t-axis, or positive v. It's above the t-axis. Then he's going backwards. Forward, backwards, he turned around. Then he turned around right there. Here's a similar example, going backwards, below the t-axis, going forwards, above the t-axis. Turns around right there. Here he's below the t-axis, so he's going backwards, and then he's below the t-axis, so he's also going backwards. He never turned around. This is not an example of turning around, but it's a common mistake. Students think it's turning around if you're not thinking about what's going on. Another way to think about this is all these velocities are negative. Velocity versus time graphs. Above the time axis means moving forward. Below the time axis means moving backwards. Going towards the time axis means slowing down. So going towards the time axis looks like this, or it could look like this. From the last rule, below the t-axis, this guy's going backwards, this guy's going forwards, but they're both slowing down. Going away from the time axis means speeding up. Speeding up, so he's going away from the time axis. His velocity is getting more and more negative. It's getting bigger and bigger, faster and faster. Here he's going forwards, faster and faster. So I would memorize that above the time axis is moving forward, below the time axis is moving backwards. And I would also memorize that going towards the time axis is slowing down, going away from the time axis is speeding up. Lastly, the concavity of the xt graphs. We talked about concave up, concave down in math class. So let's look at some positive accelerations. We can see here that the object's position is decreasing. So in terms of acceleration, we'd say that's a negative. He's going backwards. The slope, or the slope of the tangent line here, it's kind of a bad tangent line, but you'll get the picture, is decreasing. It's getting shallower and shallower. It's going slower and slower. So that's a negative sign as well. Backwards, negative. Slower and slower, negative. That gives us a positive acceleration. Next one, the slope is getting steeper and steeper, and the position is increasing. So going forward, positive. Going faster and faster and faster, positive. Gives us a positive acceleration. Now here's the tricky one. You may want to think that the acceleration changes right here, but let's check this in two different kind of regions. So here I'm going backwards, so this is decreasing, that's negative. And the slope is decreasing. So here you can see it's real steep, and here it's real shallower. So I'm slowing down. So that's a negative. Negative times a negative gives me a positive acceleration. Here I have I'm going in the positive direction. The positions are getting bigger. And also my velocities are getting bigger. You can see that this is very steep tangent line here, and it's kind of a shallow tangent line here. So I'm going faster and faster. Positive times a positive gives us a positive acceleration. So even though the graph turned around, or the object turned around, it's still a positive acceleration. Notice this title of this slide was concavity. Concave up, concave up, concave up. Positive acceleration, positive acceleration, positive acceleration. So we have a rule. Positive acceleration means concave up. For negative acceleration, I bet you can guess what this is going to be. So here we have an object going backwards, which is a negative sign, and it's speeding up, which is a positive sign. So you can see here that Here's the steepness of our tangent line, and the tangent line is steeper later on, so it's speeding up, positive sign, gives me a negative acceleration. Similar thing here, speeding or going forward, positive sign, slowing down, negative sign, negative acceleration. If we have the whole thing here, during this section we have it going forward, but slowing down. This section we have going backwards, but speeding up. Both of those are going to give us a negative acceleration. So again, the pattern, concave down, negative acceleration. Concave down, negative acceleration. Concave down the whole way, negative acceleration. So our rule is, on an xt graph, position versus time graph, negative acceleration means concave down. And that's the end of this screencast. You can go back, watch it again, you can watch certain parts again. If you understand everything on here and you have these things memorized, you should do well on the graphical part of this unit.